Hi all and welcome back. So this week we're going to be looking at software vulnerabilities. So we had a little brief look at them last week, but we're going to be looking in more detail today. So to begin with, we're going to be looking at the sources, so things that cause software vulnerabilities, where do they come from. And that'll be a bit of a recap from last video. We're then going to be looking at the categories, or one of the ways in which we can split up these different software vulnerabilities and put them in boxes. There's tons of different ways of categorizing and classifying these things, so we're going to then look at some other ways of doing it. Okay, so this is, like I said, this is a bit of a recap. This slide was in the last video I released. So software vulnerabilities generally their weaknesses in software security. So they generally come from either design problems, misconfiguration problems, or implementation problems. So we're going to be focusing on implementation problems during this module. So there are many different categories, many different ways of putting, as I said, of categorizing software vulnerabilities, but this is one way which is used by the SciBOK. This is the way the SciBOK knowledge area breaks it up. There are other taxonomies depending on whether you want to look at causes of software vulnerabilities, or there are various other ways of breaking it up. Like I say, we'll get to that later. So structured output generation. This might be a new way of thinking about certain types of vulnerabilities. So structured output generation vulnerabilities are pretty much just any vulnerability that exists in a system which allows you to input data into a program that is then used as output from that program or service or process as input into another system. So think about it like this. So that sounds very complicated, but it's not really. Examples of this is things like SQL injection. So you're able to pass data in that's immediately handled by the program and treat it as code. That it's creating a output SQL query and then passing that into a database. So it's creating some structured output, which is an SQL query, and it's generating that, and that's getting passed into a database. The database is then using that, passing data back. So if we can manipulate the process that generates the output, then we can do some things that we shouldn't be allowed to do. These vulnerabilities, other examples are things like XSS or command injection. Basically anything where we're putting data in that's then getting directly passed into another process without proper sanitization falls under this category. So race conditions. I'm just going to give a brief overview of all the categories here, and then we're going to dig into these in more detail in future videos and in subsequent weeks. So race conditions are concurrency bugs. So race conditions take place when there's when multiple processes or threads are sharing the same resources, and they're designed in a way that the correct or ideal or expected valid running of the program depends on the order that the resources were accessed by these distinct two or more separate resources. Threads or processes. So in a race condition, vulnerabilities. So in race condition vulnerabilities, resources can be accessed out of order by different threads running concurrently, and it violates the specification, the software specification, either whether it's been implicitly or explicitly defined. It violates that specification and causes a security problem. That's what happens in race conditions. Examples of this are things like time of check, time of use vulnerabilities. So imagine you had a file. A common way of doing this is using symlinks. So if you had a file that was read by a program, the program did some validation to check that the user that that is running the program actually has permission to read the file that they're reading, so it checks that. Then it does some other operations, or there's a delayed period before it actually uses the file. So one thing that you could do, an example would be if you had just a file in your home directory on a user account that was used in the running of a process that used like a setuid, that had the setuid flag, so it would run as root, but it would have some internal logic checking that you were actually able to access that program, access that file or resource. So if it did this, and then you replace the file or resource with a symlink to some file or resource that you don't have permissions with, but because it's running as SUID, it's elevated its privileges. You can then get it to do things like read data that you shouldn't be able to do, or you're basically just bypassing the access control check because of a programming mistake. Some examples in the real world are Meltdown. Meltdown was a CPU design problem, which combined, it was a massive problem that ended up leading to the full redesign of like big pieces of CPU architecture, and that combined a race condition and a side channel attack. So what's a side channel attack? Side channel attacks are vulnerabilities that occur when some feature of the environment that the program is running in leaks information that allows an attacker to infer the value of some hidden data. So think about things like, this is used often in things like cryptanalysis, or like I just said with Spectrum Meltdown, this was a cache timing attack. So what the way that Spectrum Meltdown would work would be they would try and grab a resource from the cache over and over again, and if they would essentially check if this resource was in the cache. If it was, then it would take less time to execute or to fetch it than if it wasn't in the cache. And you could do things like you could basically use this to find information that you shouldn't be able to. There's other things like power analysis, differential power analysis. So this is another thing where people have used this to try and break cryptographically secure, crypto algorithms, basically. They check how much power is being generated, and they basically assign a bit value to the power. So if it's at if a certain level of power is being used at a certain time, and then more is being used, they can infer things about the program that the program probably doesn't want them to infer. So we got API vulnerabilities. So API vulnerabilities basically occur when components of the system interface with each other via an API, and they don't correctly use the API according to the specification or the contract of how it was intended to be used. So this is again an obvious security problem when we think about things like security sensitive APIs like crypto libraries. This is the most common place that this, or one of the more common places that this vulnerability occurs, is when a programmer uses a crypto library without understanding what it does, and the system that they're attempting to secure or actually isn't secure because of their misuse. So there are others like those involved with security sensitive areas like access controls. So if you misuse an access control API, then you might leave holes in your application system. There are often other security problems that can be introduced when we're doing things like using pieces of data between two different components in a system via an API, and if they're not consistent. So you might have different sized, you might be using like two different versions of a particular specification or an API. On one end you might have a different sized variable that has later been updated in a different piece of the application to be bigger, and it's not been updated in the other piece, and then you've got problems that exist like integer overflows when you using incorrect types together. When you're trying to cast between these two variables, you might have other logic where you're like using this piece of data and thinking it's smaller than it is. Can lead to things like buffer overflows. And memory management, some buffer overflows are a memory management problem. So memory management vulnerabilities are what we're going to be focusing on in SSE. So these are things like buffer overflows, things like use after free vulnerabilities, things like double freeze. These are all problems where the programmer has incorrectly managed memory. So either they are, it could be that they're not correctly checking how much memory they're putting into variables, or it could be that they are not correctly allocating and deallocating memory, and they're not correctly getting rid of things like dangling pointers. We'll go into this a lot over the course of the next few, of the remainder of the module. Okay, so some of the classifications. There are two good ones that we're going to look at today. So first off, MITRE has a way of classifying weaknesses in applications and systems, and they call it common weaknesses enumeration. It's the CWE, and this there's also NIST put together a way of, at a glance, a quick way of identifying how severe software vulnerability is. So there's a common, they use the Common Vulnerability Severity Score, CVSS, and this has two components. One is that it is just it can be represented in two ways. One of the ways it can be represented is just a number less than 10 with one decimal place, or 10. 10 is the max for the most severe vulnerabilities. And there's also a vector string, and the vector string's like a shorthand way of expressing the different parts of an attack that we might be interested in terms of severity. So things like the attack vector. So did this attack, is this vulnerability exploitable over the network, or is it only local, or is it only via adjacent networks? Things like how complex is it? We'll look at that in a minute. So first, I'm just going to walk through. We'll have a look at CWE. Okay, so this is the. Let's just go back to the first page. All right. So there's a few, as you can see, there are. They advertise these three different ways. Let me show my cursor. Sorry about this. It's gone. Alright, forget it. Won't bother with the cursor. Up here somewhere. Right, yeah, so there's a few different ways of breaking it up. So you've got, these are the most useful. So you've got three different ways of looking at the lists of weaknesses. So I'll just have these three just for now to show you the difference. So if you want to look at it from a software development perspective, it's broken down by lots of different software concepts. So things like APIs and function errors. So we just saw that was one of the categories that Cyborg uses to break it up. So these are things like using dangerous functions, Example of that we're going to be looking at next in the next video and next week. So things like the printf function, incorrectly using that, or things like getS, C functions that are well advertised to have security problems with them, and they're either very difficult to use securely or just plain broken altogether. They recommend, if you look in the man pages, it's quite funny actually, if you look in the man page for getS, there's a big warning saying do not use this function. So some of these things are left in, like it's still in libc for backwards compatibility reasons. But yeah, we'll have a look at that properly next time. So we'll look. So there's other things here we can see. So we've got things like this concurrency issues, and we can see race conditions, time of check to time of use. There's things. What else can we find? Can we find side channels? Communication channel errors. Yeah, so covert timing channel. There's like information management errors. So yeah, observable timing discrepancies. So this is what the cache timing attacks would fall under. So there's loads of different ways. So there's loads of different ways of doing this. If you see up at the top of the list, it says that there's 916 weaknesses. So this list view shows you lots and lots of different ways of looking at it. So there's things like the OWASP top 10 are in here. If you click on that, they've sorted all their objects by the OWASP top 10. So these are some really interesting, useful things. Research concepts. So this is more like things that we see in SciBoc, things like access controls or control flow management. So if we look in string errors, we can find the format string vulnerability. So we'll take a look at what we get if we click on one of these vulnerabilities. So we have things like just a brief description of this type of weakness, and it goes into more detail. So if we're looking at format strings, it can lead to things like buffer overflows, denial of service, and it's a problem because it accepts a format string. We'll find out what that means next video. And it originates from an external source. So here we have things like it shows you which ways they've grouped it together as well. If you look at this relationships, if you're interested in that, there's various like 7 pernicious kingdoms. This is a taxonomy. This is another way of putting it all together. A taxonomy for software vulnerabilities. So we'll go back to the format string. I'll get rid of all this. So it shows you how. So there's the section for how it was introduced, modes of introduction. It tells you that, and there's some. So it's introduced at the implementation phase. So it's an implementation bug, like we're focusing on this time. It tells you what languages that it's prevalent in. Things like the scope, so what's impacted, so confidentiality is impacted, and then likelihood of exploit, and then we get some nice example code that show you. We can actually use this one in the next video. So this is an example of exploitable code. We'll actually go through this one and exploit it. We'll show you what the problem here is. The problem is essentially that this function we can. Because we control this variable, there are certain characters we can put in so that we can actually read from memory and write to memory, and we can do that by controlling this input. So that's obviously going to lead to massive security problems. It's a memory management problem, but it's also an incorrect use of a function. So it's like a kind of an API problem as well. So like these things don't always just fit straight into one box. It's usually a bit of both. Other things. All right. So here we have like examples of CVEs, which is pretty cool. And mitigation tells you how do you mitigate against this problem, and there's various different phases you can mitigate against it at. So the implementation phase, they want to make sure that all format strings are past a static string, which cannot be controlled by the user. Right. So we don't want to give the user control over this function that has the capability of reading and writing to arbitrary memory. It's a problem. We can start doing things like writing shellcode into memory and like messing with return pointers, or like the things that control the instruction, the things that determine the control flow of the program. So let's just click on one of these CVEs. We'll try and find the CVSS score and go have a look at that. So MITRE are the people who run NIST. MITRE are the people who run CWE. The common weaknesses. They host this common weaknesses and enumeration list of weaknesses. They also host this common vulnerabilities and exposures, the CVE numbers. And okay, so we can see that the National Vulnerability Database. So we can have a quick look through here. There's a bunch of references. It tells you that there's a format string vulnerability in the ToolTalk database. So this was in 2001, so it's quite old, quite an old vulnerability. But it allows remote attackers to execute arbitrary commands by a format string specifier that's passed to the syslog function. So we've got remote code execution basically, which is as bad as it gets. So let's have a look on there. Look at the NVD and we'll see if we can get an example. Yeah, alright, so there's none there. Right, yeah, because it's an old one, nobody's actually filled in the score using the newer version of the CVSS, but we've got an example here. So base score 10.0, high. We can click on that to see we can see what it means, and we can see that this is, I'll go back actually, it's probably easier here. Alright, so this vector string is what I mentioned at the start. So this gives you an at a glance way of seeing why it's got this score of 10. So with 10, it's obvious. With 10, you know it's basically remote code execution with no. So let's have a look. So there's so it's low complexity. So if we see here, there's the list of, so the string starts with a identifier, so something like AV means access vector, AC is the access complexity, AU is does it require authentication or not, confidentiality is C, so integrity is I, and availability is A. So what do they mean by, what are the options for these? So for the access vector, well, we can click through here actually, it gives you the options. So if you mouse over them, it gives you a nice description of what it means by each of these things. So authentication, if you mouse over then no authentication is required to access and exploit the vulnerability. So it doesn't require you to already have an account on the system or be past a certain point of maybe there's a vulnerability on the admin page or something, which you can only get to if you have a certain access permissions. Maybe you need a cookie or something on a web app. I don't know, something like that. Single means you would need to auth once. Multiple, you need to do a bunch of things. So the complexity is pretty straightforward. How complex is the exploit vulnerability to exploit? Confidentiality, does it leak any information? Does it leak some information? Is it complete system breach? Availability, does the resource that we're affecting persist after we exploit the vulnerability or not? This can totally, basically, can the attacker take the system offline with this vulnerability or not? And integrity, so you've got confidentiality, integrity, and availability, the CIA triad. So how are they affected, and then how complex is it to exploit. Basically, that's the way that they're looking at how severe a particular vulnerability is. These are some other I guess this is for. These are some additional ways, like temporal, so time-based stuff, or environmental. But these are the main ones. The base core metrics are the ones that we see mostly, and the ones that are represented in the vector string. All right, so hopefully that was interesting. We'll be looking at format string vulnerabilities next time, format string attacks. So, cheers.